Hey everyone, this is lesson 3-3. Today we're looking at increasing and decreasing functions and something called the first derivative test. So over the next couple of lessons, we're really going to focus on how we can use the calculus you've learned to analyze the behavior of the graph of a variety of functions. Today we're focusing specifically on increasing and decreasing behavior. And to make sure that we sort of are all starting in the same place, let's give a formal definition here to what it means for a function to be increasing or decreasing. Now, you do not need to write this down. In fact, I don't even want you to spend time writing this down. This is just to make sure that we're all clear what I do mean by increasing and decreasing. So really, you just need to understand this at an intuitive level. So a function f is increasing on some interval I if x2 greater than x1 implies that f of x2 is greater than f of x1 for all values of x in that interval. Long story short, as x gets bigger, y should also be getting bigger. That's what that's basically saying for increasing. And then decreasing is similar to that. So a function f is decreasing on some interval I if x2 greater than x1 implies that f of x2 is less than f of x1 for all x in that interval. So in other words, as x gets bigger, the y values actually get smaller or lower. Okay, so visually, this is just an example of what we mean by increasing and decreasing. So notice for the increasing graph, as x gets bigger, the y values get higher. And for decreasing, as x gets bigger, the y values get smaller. Notice in both cases, we're really talking about as you're looking at the graph from left to right, because we're talking about as x gets bigger. So as you follow the graph from left to right, the graph is rising for increasing or descending for decreasing. Okay, so what I want us to look at then is for this increasing graph right here, if I were to draw in a few tangent lines along this graph. So if I were to sketch all these tangent lines, all of those tangent lines, and specifically all of the slopes of those tangent lines, have something in common. Can you figure it out? Well, if you said that all of those have positive slopes, that is exactly right. So for an increasing function, notice that all of the tangent lines have a positive slope. Similarly, for decreasing, for all of these decreasing tangent lines, oops, missed on that one. All of those tangent lines for a decreasing function also have something in common with their slopes, and that is that all of those slopes are negative. Okay, so let's think about that for a second. So if a function is increasing, so if f is increasing, then that means that its tangent lines have a positive slope. But remember, in this course, the slope of the tangent line is better known as the derivative. So what that means is that if a function is increasing, then that means that f prime is positive. And then similarly, if a function is decreasing, so if f is decreasing, then we just saw that that meant that its tangent lines have a negative slope. But again, if we're talking about the slope of the tangent line, then we are talking about the derivative. So that means when a function is decreasing, its derivative is negative. So what that allows us to do now is it allows us to make this connection between the calculus that you've learned and the increasing or decreasing behavior of a function. And so that leads us to this theorem here. So please do write this one down. So let f be a function that is continuous on the closed interval from a to b and differentiable on the open interval from a to b. If f prime of x is greater than 0, meaning if f prime is positive, for all values of x in that interval, then that means f is increasing on that interval. Again, remember that we just saw that when the function was increasing, all of its tangent lines had a positive slope. But the slope of the tangent line is the derivative. All right, if f prime of x is less than 0 for all x in that interval a to b, then that means f must be decreasing on that interval. And then finally, if f prime of x is equal to 0 for all values of x in an entire interval, so not just at a single point, but in an entire interval, if the derivative is constantly 0, then that means f has to be constant. That means that the function, the graph of the function, must be a horizontal segment at that point, or on that interval. All right, so that's the theorem that we're going to use for this first example here. All right, so here we go with the first example. State the intervals on which f of x equals x cubed minus 9 halves x squared is increasing or decreasing. Okay, so this is our chance to apply the theorem that we just talked about. Now remember, in order to determine where this function is increasing or decreasing, we need to take a look at its derivative and determine where is that derivative positive and where is that derivative negative. So first thing we need to do is find the derivative. Okay, so f prime of x, we just have to use the power rule here. So f prime of x is going to equal 3x squared minus 9x. Okay, now, next thing we're going to do, find critical numbers. Find critical numbers. And actually, before we even do that, first thing I should have mentioned is we do need to actually take a look at domain. Now, this is a polynomial. I kind of just skipped right over that, but remember, for a polynomial, we know that the domain is going to be all real numbers. But we do want to make sure that we take a moment to think about the domain, specifically if there are any domain restrictions, because that is going to play an important part in one of the latter parts of this process. Okay, so now that we have our f prime, let's find our critical numbers. So that means we need to set our derivative equal to 0, or find where our derivative is undefined. Well, we know it's a polynomial, so this is never going to happen, but we have to at least consider it. For equaling 0, we've got 3x squared minus 9x equals 0. We can factor out that 3x. And then now we can finish solving this by factoring. So 3x equals 0, or x minus 3 equals 0. So that does give us x equals 0 and x equals 3. So those are our critical numbers. And again, f prime is never going to be undefined, so we don't have to worry about that. Okay, so now to figure out where f is increasing or decreasing, again, we have to look at the signs of f prime. We have to figure out on what intervals is f prime going to be positive or negative. So to do that, we're going to make a sign chart. Now, you've probably learned how to make a variety of sign charts over the last several years of mathematics. So I'm going to show you one version of a sign chart. You don't have to format your sign chart exactly the same way that I show here. It just happens to be the way that I do it. So if you have a different format that works best for you, please feel free to stick with that. But you're going to see me do my sign charts in this particular way. So here's how I'm going to do it. So I'm going to leave myself some space above what I'm about to write. So I'm going to start by writing out just a little number line. Well, I'm using the word number line loosely. And on this number line, I want to indicate, in numeric order from left to right, any critical numbers and any domain restrictions. Now, we didn't have any restrictions on this one, but if I did, if I had maybe a place that would make my denominator 0, so any domain restrictions would also be included here. So again, we're going to include critical numbers and domain restrictions. Okay, so for this one, all that I had was 0 and 3. So again, I'm going to put the 0 on the left side because that's smaller, and I'm putting 3 on the right side because that's larger. Now notice I just kind of spaced these out evenly. When I said number line and I said I was using that term loosely, I'm not going to worry about putting like a 1 and a 2. I literally just want to know where those critical numbers are and those domain restrictions, because what I'm really doing is I'm just setting up endpoints of intervals. In other words, on this number line, by putting those two critical numbers, I've now divided my number line into 3 distinct intervals. I have the interval from negative infinity to 0, from 0 to 3, and from 3 to infinity. And the reason we do that is those are the intervals where the behavior of the graph of the function can now change. And so those are the intervals where f prime might change signs, and that's what it is that we're trying to look at. So now that I've labeled my fake number line, I'm going to draw 2 rows above that. And then I'm just going to go ahead and draw the columns that line up with those critical numbers. Now, the top row is where I'm going to analyze f prime, the derivative. The bottom row is where I'm going to use my analysis of f prime to conclude the behavior of f. Okay, again, this is just how I do my sign charts for this. You don't have to follow it exactly. If you see a different way, that makes more sense to you. Okay, so now, again, for f prime, I'm just trying to figure out positive or negative for each interval. So I'm just going to randomly pick any value that I want from negative infinity to 0. So, choose something easy. So x equals, let's say, -1. Now, if I'm trying to fill in the row for f prime, then that means I need to use the equation for f prime. Now remember, f prime was 3x squared minus 9x, but I'm going to actually use the factored form of 3x times x minus 3. Because if I'm dealing with factored form, that's a lot faster when you're trying to figure out signs. So if x is -1, then 3x is going to be a negative, and x minus 3 is also going to be a negative. And a negative times a negative gives me a positive. So on the interval from negative infinity to 0, f prime is positive. Okay, we're going to do the same thing here now between 0 and 3. So let's maybe use x equals +1. So in the derivative, that's going to be 3 times a +1, which is going to be a positive. And then 1 minus 3, which is going to be negative. So I have a positive times a negative, and that is negative. And then finally on that last interval, greater than 3, so let's do maybe 4. Okay, so if x is 4, 3 times 4 is going to be a positive. Again, notice I don't even care what the actual number is. I just care whether it's going to be positive or negative. That's why factored form is so nice, because all we're worried about is whether I'm multiplying a positive or a negative with another positive or negative. So positive times 4 minus 3, that's also positive. So positive times a positive, and we get positive. All right, so now we can use the theorem. So according to the theorem, if f prime is positive on some interval, then that means f is increasing. Now there are a couple ways you can indicate this. You can actually just put like INC for increasing. I actually like to draw a little arrow that's going up to the right, like an increasing graph. And then from 0 to 3, f prime is negative, so again that means that f must be decreasing. So I'm going to draw a little arrow that's going down to the right, like a decreasing graph. And then finally on the last interval from 3 to infinity, f prime is positive, so once again, that means f must be increasing. The reason I like to draw those little arrows is because that's actually giving me a little visual of what the graph is doing. So according to this picture, the graph is going to increase until I get to x equals 0, and then it's going to decrease until I get to x equals 3, and then it's going to increase again after 3. Okay, so that's what this table is telling us. All right, so now we actually just need to answer the question. It says to state the intervals on which this function is increasing or decreasing. Okay, so that means for increasing, we know that this function is increasing on the interval from negative infinity to 0, union, and then also the interval from 3 to infinity. And then for decreasing, we know that this function is decreasing on the interval from 0 to 3. Okay, so that is how we use that theorem where we've used the first derivative and its sign to determine whether the graph of the original function f is increasing or decreasing. Now, one of the things that I showed when I sort of sketched the graph of the behavior was that. Now, there's something that we talked about back in lesson 3-1, and that is, remember that the top of a hill or the bottom of a valley, those were critical numbers. More specifically, this point right here is actually a relative maximum, isn't it? And then this point down here, this is actually a relative minimum. And notice that that's where f prime changed from positive to negative or from negative to positive. So what that means then is, not only can we use the first derivative to help us determine where a function is increasing or decreasing, but we can also use the behavior of the signs of f prime to determine where we might have a relative maximum or a relative minimum for the graph. And that's going to take us to what's called the first derivative test. Okay, so there is a lot of words here for the first derivative test. I do need you to know what it says, but whether or not you take the time to write this down word for word, I'm going to leave that up to you. Again, what's important is that you know what this first derivative test is saying. So let C be a critical number of a function f that is continuous on an open interval containing C. Okay, so again, we're specifically talking about at critical numbers. again, that's a place where the derivative is equal to 0 or undefined, but the original function is defined. Remember, a critical number is in the domain of the original function. Okay, so if f is differentiable on that interval, except possibly at c, and I'll explain why they put that indicator in there, then f of c is a relative maximum of f if f prime changes from positive to negative at x equals c. Now that should make sense to us. If f prime changes from positive to negative, so again, if f prime changes from positive to negative, then remember that that means f is going from increasing to decreasing, which means we've got the top of a hill. And that's why we would have a relative maximum there. All right, similarly, f of c is a relative minimum of f if f prime changes from negative to positive at x equals c. And again, hopefully that makes sense. If f prime changes from negative to positive, then that means f is now going from decreasing to increasing, so we now have the bottom of a valley, which is a relative minimum. And then finally, if f prime does not change signs at x equals c, then that means f of c is neither a relative maximum nor minimum. That should say nor. Okay, and again, if you think about what that means, so if f prime, let's say f prime is positive, and then it hits a critical number, but then it stays positive, that means your function is increasing. It instantaneously levels out, but then it continues to increase. The most common example of that is the origin of an x cubed function. So this graph is increasing. It levels out for just a moment at x equals 0, but then it continues to increase. So that's an example of what this would be describing here. Okay, so this is the first derivative test. So to look for where a function has a relative maximum or a relative minimum, we're really just looking to see where does the derivative change signs. Okay, but again, that has to occur at a critical number, not at, say, a vertical asymptote, because remember, you can't have a relative max or relative minimum at a place where the graph doesn't actually exist. Okay, so we're going to look at several examples using this theorem here. Okay, so we're going to state the intervals on which the function is increasing or decreasing, so that's exactly what we already did on the first example, but then we're going to go ahead and take it one step farther and say locate and classify all relative extrema. So when they say locate, they mean to give the coordinates, and when they say classify, they do want us to specify, is it a relative maximum or relative minimum? Okay, so here we go. So same process. Here's our function. First thing we want to do is take note of the domain. Well, this is just a polynomial, but it's in factored form, but that means our domain is still going to be all real numbers. So we have no domain restrictions in this particular case. But now we do need to find the derivative. All right, so f prime of x equals, this is a product, and in that product we are going to have a chain rule here. So I've got the first times the derivative of the second plus the second times the derivative of the first, which is going to be 2 times x plus 2 to the first times the derivative of x plus 2, which is just a 1. And when I clean this up a little bit, I'm going to have x plus 2 squared plus, let's see, I'm going to put the 2 and the 1, that's going to be a 2. I'm going to put that in front, times an x minus 1 times an x plus 2. Now, in the previous unit, you would stop here oftentimes, and this would be fine. But again, for our purposes here, we do actually want to take this farther, because remember, we're trying to set this equal to 0 and solve, and that means we need factored form. So hopefully you recognize we do have two terms here. Both terms contain a common factor of x plus 2. So I am going to factor out an x plus 2. That is going to leave me with another x plus 2 in that first term, plus a 2 times an x minus 1 from the second term. Notice that x plus 2 is now gone out in front. Okay, so now I've got that x plus 2 times, and then here in the parentheses, or in the brackets, I have x plus 2 plus 2x minus 2. And when I clean this all up, I have x plus 2 times, all right, so x plus 2x is going to be 3x, and then the 2 minus the 2, those cancel out. So this is our factored form of the derivative. All right, so now when I'm setting this equal to 0, I've now got x plus 2 times 3x equals 0. So that means x is going to equal negative 2, or x is going to equal 0. Okay, so, and again, f prime, of course, is never going to be undefined, but I don't want to forget about at least considering that. So now let's go ahead and make our sign chart, just like the last time. So in this sign chart, again, I had no domain restrictions. If I did, I would include those on here as well. But then I have my critical numbers at x equals -2 and x equals 0. So here's my -2, here's my 0. Again, remember, -2 is smaller, so it has to be on the left, because this is a number line, because we're setting up intervals. All right, and then we need our 2 rows. The top row is for f prime, and the bottom row is for f. All right, and now we're going to do our analysis here. So for this first interval, from -infinity to -2, so let's maybe use x equals -3. So if I substitute x equals -3 into f prime, and again, I'm going to use this factored form down here. So remember, we're really looking at f prime of x equals 3x times x plus 2. So if I put -3 into this, I'm going to have a negative times a negative, and that is going to be a positive. Between -2 and 0, so -1. If I substitute -1 into f prime, that's going to be a negative times a positive, which is going to be a negative. And then if I substitute something greater than 0, so maybe x equals +1, that's going to be a positive times a positive, which is a positive. Okay, and then according to our theorem earlier, since f prime is positive on that first interval, then that means f must be increasing. On the second interval, since f prime is negative, then that means f must now be decreasing. And then on the last interval, since f prime is positive, f must be increasing. Okay, so now we have lots of things we need to write out to answer this particular question. So remember, first, it asked for increasing intervals. So according to our sign chart up here, we know that f is increasing on the interval from -infinity to -2, and from 0 to infinity. And then we know f is decreasing on the interval from -2 to 0. All right, so now we can think about the first derivative test. So notice at x equals -2, notice that f prime is changing from positive to negative. And that means f is going from increasing to decreasing. And that means we must have a relative max at x equals -2. So we have a relative max at x equals -2, but I need to know the y-coordinate, because remember, I'm trying to state the point. So if I need to know the y-coordinate, that means I'm substituting back into f. So f of -2, well, that's going to be -2 plus 2 squared times -2 minus 1. Well, -2 plus 2, that's going to be a 0 anyway. So this whole thing just goes to a 0. So our relative maximum is at -2, 0. Now, I have to stop here for a second. This is a visual trick. Remember, these are intervals, meaning this is talking about all values of x from -infinity to -2 and all values of x from 0 to infinity. This is an interval saying all values of x from -2 through 0. This, however, is the ordered pair, -2, 0. This is an x and a y. So it is important that you notice the context of what we're writing, because on this first one, this is an interval. This right here is a coordinate. Okay, so please be very careful about that. Now, notice at x equals 0, notice that f prime is changing from negative to positive, which means f is going from decreasing to increasing. And that means that at x equals 0, we must have a relative minimum. Okay, so we have a relative minimum when x is 0. And again, now I need to know the y-coordinate. So f of 0, well, that's going to be 0 plus 2 squared, and then times 0 minus 1. Well, 0 plus 2 is 2, 2 squared is 4, and then 4 times -1, and that gives us a -4. So this is now happening, the relative minimum happens at the ordered pair 0, -4. And all of that is our answer for this question. Okay, but again, notice, for the increasing and decreasing, those are intervals. For relative maximum and relative minimum, those are coordinates. Okay, so please, please, please be careful that you don't get tricked by that, okay? All right, let's move on and try another one. Okay, this time we have f of x equals x squared over x squared minus 4. All right, we have a rational function, so we definitely have the opportunity for some domain restrictions here. And in fact, that denominator can definitely be 0 a couple of ways. So for our domain this time, we know that x cannot equal plus or minus 2, because positive 2 and negative 2 would both create a 0 in the denominator. Okay, so remember, that does mean when we get up to our sign chart, we are going to include positive 2 and negative 2, not because they're critical numbers, but because they are domain restrictions. Okay, so now let's find our critical numbers by finding the derivative. I'm going to go ahead and use the quotient rule here. So I've got low d high minus high d low all over low low. And so this is where we do need to take some time and simplify that numerator. So I'm going to distribute that 2x, and now I've got a 2x to the third minus 8x minus a 2x to the third. And then that's all over x squared minus 4 squared. Well, the 2x cubes cancel out. And so finally, I just get negative 8x over x squared minus 4 squared. Okay, so to find our critical numbers, once again, we're setting f prime equal to 0, or we're setting f prime to undefined. Well, f prime is a quotient, it's a fraction, so we know that that can equal 0 if the numerator equals 0, and that's going to happen when x is 0. So there's one of our critical numbers. And we know that f prime is going to be undefined when that denominator equals 0. But that's going to happen when x squared minus 4 equals 0, and that's going to be when x squared is 4, when x is plus or minus 2. But remember, those are not critical numbers, those are domain restrictions. Okay. So all we had for critical numbers was x equals 0. We had additional domain restrictions at plus or minus 2. So now let's go ahead and make our sign chart. And you're going to see me do something a little bit different on this sign chart. And I'll try to explain why in just a moment. Okay, so I've got 3 numbers I need to include here, right? 2 domain restrictions and 0, which is our critical number. So negative 2 is the smallest of all of those. So I'm going to put negative 2 first, and then 0 comes next, and then 2 is the largest. So notice this time around, we actually have 4 intervals that we're going to have to analyze. Negative infinity to negative 2, negative 2 to 0, 0 to 2, and 2 to infinity. All right, so once again, let's draw our 2 rows for f prime and f. Draw our columns there. So this is f prime, and this is f. Now, I am going to show something that I didn't do on the previous ones that I really could have and probably should have, but now you'll hopefully understand a little bit better how come I'm doing this. Remember, negative 2 is in this sign chart because it was a domain restriction. This actually made f and f prime undefined. And the reason I like to do that, if later on in this process, in this problem, if later on f prime changes signs at negative 2, if I don't show this undefined symbol, I might accidentally think that I actually have a relative maximum there because I see that positive to negative sign change. But remember, negative 2 is not a critical number, it's a vertical asymptote. So I need to remind myself that f and f prime are not actually defined there. So hopefully that would prevent me from mistaking negative 2 as potentially being a relative maximum or a relative minimum. So same thing with positive 2. This is going to actually cause both to be undefined. Now 0, remember 0 actually made f prime a 0, which is fine, right? That's exactly what we're looking for. Okay, so now we can do our analysis for f prime. So let's go ahead and choose a number smaller than negative 2. Actually, before I do that, let's take a note about f prime. So for f prime, notice the denominator is getting squared. And that means as long as our denominator is not 0, if I'm squaring that denominator, this is always going to be positive. And what that means is when I'm trying to figure out whether f prime is positive or negative, I don't really have to consider the denominator here because dividing by a positive isn't going to change anything. So really, all I have to do is just focus on what happens in the numerator. Because whatever sign I get from the numerator, dividing it by a positive isn't going to change that. So for this first interval from negative infinity to negative 2, if I use negative 3, well, that means I'm going to have negative 8 times a negative 3, which is going to be a positive. And again, I don't have to worry about the denominator because that's always going to be positive. From negative 2 to 0, let's go ahead and use negative 1. So negative 8 times negative 1 is going to be a positive. Between 0 and 2, let's use positive 1. Okay, so I have negative 8 times a positive 1. That's going to be a negative. And then bigger than 2, let's go ahead and use x equals 3. So negative 8 times a positive 3 is going to be negative. Okay, so that means on that first interval, since f prime is positive, f must be increasing. On the second interval, from negative 2 to 0, f prime was positive, so that means f is still increasing. 0 to 2, f prime is negative, so now f is decreasing. And finally, from 2 to infinity, f prime was negative, so f continues to decrease. So now we can finally answer the question. So on what interval or intervals is f increasing? Well, it's increasing. F is increasing from negative infinity to negative 2, and then from negative 2 to 0. Now, some of you might be wondering, could we just say negative infinity to 0? And we can't, because remember, if I said negative infinity to 0, I am now including negative 2. And the problem is, remember that the original function is undefined at negative 2. So I cannot include negative 2 in any of these intervals because the function is undefined there. For decreasing, well, this function is decreasing from 0 to 2, and then again, separate this from 2 to infinity. All right, now, we did not have a sign change at negative 2, which even if we did, it doesn't matter, because remember, negative 2 was a domain restriction. So even if I had a change of signs there, that does not give us a relative extremum. But at x equals 0, f prime does change from positive to negative, which means f changes from increasing to decreasing, and that means at x equals 0, we do have a relative maximum. So we have a relative maximum when x is 0, and then that means we're going to go back to the original function, f of 0, well, that's going to be 0 squared over 0 squared minus 4, and that's just going to be a 0. We do not have a relative minimum because at no place do we have a change in signs for f prime from negative to positive, and we don't have any critical numbers where that happens. So for relative minimum, we can say none. If it doesn't prompt you to type anything in, I can't quite remember exactly what you're going to be asked to do on WebAssign, so if it asks for a relative minimum, of course you would say none here. If it doesn't ask for it, you just don't type anything in. Okay, and that's how we approached that problem. So again, the big deal with this particular example was we did have a couple of domain restrictions that we needed to include in our sign chart, and I wanted to make sure that you saw how we dealt with that. All right, one more example of this particular topic. So we have g of x equals sine squared of x minus cosine of x, but this time we're on the interval from 0 to 2 pi. Now remember, this is not necessarily the domain. This is just telling us on what restricted interval we're analyzing this function. So I still need to consider the domain. Now, however, we're dealing with sine and cosine. Remember, sine and cosine are both continuous everywhere, and they are defined everywhere. So our domain for this function is all real numbers, but again, that's only within the interval from 0 to 2 pi. Okay, so let's start by finding our derivative. Well, first let me rewrite g of x. Remember, this is really the sine of x squared minus the cosine of x. So that does mean that g prime of x equals, so we've got a little chain rule here, that's going to be 2 times sine of x to the first times the derivative of sine, which is cosine. And then the derivative of cosine of x is negative sine of x, and then the negative and the subtraction become a plus. And so there's our derivative. But remember, we do want this in factored form because that's going to make things much simpler for us. So I can factor out a sine of x, and that's going to leave me with 2 cosine of x plus 1. So that's our g prime of x. All right, so now we can set g prime equal to 0, or set g prime to undefined. But again, because our g prime is only in terms of sine and cosine, this will never be undefined. However, this is factored, so this is definitely possible to be a 0. So that means we need sine of x to equal 0, or we need 2 cosine of x plus 1 to equal 0. Now, on the interval from 0 to 2 pi, sine of x is going to equal 0 at pi. Again, it does equal 0 at 0 and at 2 pi, but notice that we're not including the endpoints there. Okay, so only pi. And then here, again, if I subtract the 1 and divide by 2, I get cosine of x equals negative 1/2. And that means that we need cosine to be negative, so that's quadrants 2 and 3. And if cosine is a 1/2, then that means we're the 60-degree reference angle. That's the tall triangle. So that means x is going to equal 2 pi thirds and 4 pi thirds. Okay, so those are all the critical numbers that we've got. Now, here's the difference. So far, you've seen me doing our sine charts where I put arrows on the ends, and that's because we're actually going from negative infinity to infinity. On this one, however, remember, we're not. We have a restricted interval that we're looking at. We're starting at 0 and ending at 2 pi. So instead of putting arrows, I'm actually going to put lines to show that we're actually stopping at those endpoints. And then I've got these 3 numbers here. So remember, 2 pi thirds is the smallest of them. And then pi. And then 4 pi thirds. And then we've got our 2 rows for our function. Oops, this is g, not f. All right. And there we have it. So we've got 4 intervals that we're analyzing here. Okay, so now, between 0 and 2 pi thirds, well, basically, remember, this is just quadrant 1. And in quadrant 1, sine is positive, and cosine is positive. So this is a positive times a positive, which is positive. Now, between 2 pi thirds and pi, well, that's actually quadrant 2, but we do have some specific values we need to look at. So let's see, between 2 pi thirds and pi, so we can use, let's go ahead and use 5 pi over 6. Okay, so we know that sine is going to be a positive. Now, cosine of 5 pi over 6, remember, is going to be a negative root 3 over 2, and then we're going to multiply that by a 2, which is going to cancel that. I have negative root 3 plus 1. But negative root 3 is less, meaning it's farther to the left, than negative 1. So negative root 3 plus 1 is still going to be a negative. So I have a positive times a negative, and that's going to be a negative. Between pi and 4 thirds, we have the same deal going on, except this time, sine of, let me go ahead and do this, 7 pi over 6. So sine of 7 pi over 6, that's now negative. Cosine of 7 pi over 6, this whole thing is going to analyze the exact same way we did with 5 pi over 6. So that's also going to be a negative. So we get a positive there. And then finally, 4 pi thirds to 2 pi, well, we can just use quadrant 4. And in quadrant 4, remember, we know that sine is going to be negative, but we know cosine is going to be positive. So this is going to be a negative. So g prime changes from positive to negative, and then negative to positive, and then positive to negative. So we know that g is increasing, and then decreasing, increasing, and decreasing. So we can finally answer this question. We can say that we know the function is increasing on the interval. Now, this is why it was important for me to make sure we made it clear that we're starting at 0. This is not increasing from negative infinity to 2 pi thirds. That would actually be an incorrect statement. This is from 0 to 2 pi thirds. And then from pi to 4 pi thirds. And then decreasing from 2 pi thirds to pi, and then from 4 pi thirds to 2 pi. Now, we do have a relative maximum. Remember, anywhere that g prime changes from positive to negative. We actually have that happen at 2 pi thirds and at 4 pi thirds. Now, to find those y coordinates, let's go ahead and substitute back in. So g of 2 pi thirds, well, that's going to be sine of 2 pi thirds squared minus the cosine of 2 pi thirds. Now 2 pi thirds again, is right there. That's a negative 1/2 for the cosine. It's a √3/2 for the sine. So sine of 2 pi thirds is √3/2. When you square that, that's going to be 3/4 minus, and then the cosine of 2 pi thirds is a negative 1/2, so plus 1/2, which is really a 2/4, so we get 5/4. And then at 4 pi thirds, so we've got the same idea going on here with 4 pi thirds, except now it's the upside down one. So that's a negative 1/2 and a negative √3/2. But again, sine of 4 pi thirds, negative √3/2. Once I square it, that's going to become positive again. Minus the cosine of 4 pi thirds. Again, that's still a negative, so it's going to be adding. So we actually get the same exact value. And then we do have g prime changing from negative to positive at pi. So we do have a relative minimum when x is pi. So g of pi, well, sine of pi, remember, is 0. 0 squared is still 0. Minus the cosine of pi. Now, cosine of pi, though, is negative 1, but we're taking the opposite of that, and we just get positive 1. All right. And so that's how we use the first derivative test. Okay, and just to wrap this up, so one last thing that I want to try to have you start to do is to start thinking about the connection between the graph of the function and the graph of the derivative, or at least the behavior of the graph of the derivative. So, for example, right here I have some graph of a function f of x, and I'd like us to try to think a little bit about what does the graph of f of x, what does that tell us about what the graph of its derivative must look like? Now, connecting that to what we've been talking about, notice that f of x is increasing along this entire interval up until we get to this point here. So right at this point here, this is where f is increasing. So let's see, this is at negative 2 right here when it crosses the x-axis, so this is somewhere between negative 1 and negative 2. So if you think about what we've been doing so far, we know that f is increasing up until negative 1 point, oh, I don't know what that is, maybe negative 1.4-ish. Okay, so just a bit of a estimate there. Okay, now what does that mean about f prime? Well, if f is increasing, then remember we know that f prime must be positive on that interval. Okay, now we notice that f is decreasing from this point up here until we get to this value right here. So that means from negative 1.4-ish to 0, we can see that f is decreasing, which means f prime is going to have to be negative on that interval. And then finally, everything after 0, we see that f is now increasing once again, which means that f prime is now positive. So what does that mean for us then? That means the graph of f prime, so here's that negative 1.4-ish. Remember that f prime is going to have to be positive until we get to that value. And then it's going to be negative, meaning below the x-axis, until we get to 0. And then f prime has to be positive again. So again, this is now the graph of f prime. F prime is positive, meaning it's above the x-axis. And then f prime is negative, meaning it's below the x-axis. And then f prime is positive again, meaning it's above the x-axis. And in fact, this hopefully makes sense. If you look at this graph on the left, hopefully you recognize that that's a cubic function, meaning it's to the third power. And the derivative of a cubic function is going to be a quadratic function, which is what this graph kind of looks like. All right, so that is something that you are going to want to start to take into consideration. We are going to work more on this connection between the graph of f and the graph of f prime as we get toward the end of this part of Unit 3. Okay, all right, good luck.